This is a recorded video for April the 6th. The topic is on surface integral. Before talking about the surface integral, and I want to go over a little bit about the standard integration, one variable integration we know how to compute, and how we move from the standard single variable integration to the line integral. So the top left of the slide showing what is the meaning of the single variable integration given by integration from a to b of a function fx over x. So this figure shows the physical meaning of the integration. You basically compute the area of the shaded area. This is the area of the shaded area under the curve defined by this fx, and I computed the surface as the area of the shaded area from a to b. Okay, that's what the integration means. So we know how to compute that pretty well. Now, how do I compute the line integral? So line integral is a little bit different from the previous one. So this one we can consider the integration from a to b. This is sort of a straight line from a to b. Now the line integral, we don't integrate just from the x-axis. We integrate from, let's say this is my xy domain. So I have a line. Okay, this is my line C, and starting from A, this is the starting point, and I have an ending point. So I can define a line. Now, if I also have a given field, okay, a vector field, which means the vector field means for every point in this area, I can define a vector associated with a point. So I could end up having many different vectors, and which will tell sort of the flow of the field. Okay. Now the line integral says, okay, I'm going to compute the line integral says typically given by this form is integration of the over a line. This line C over here. And this f is the field. This is a vector field, okay, defined as the green color, for example. So typically for the 2D space, the vector field can be written as f1 xy, f2 xy. So for every point, this is xy, for example. So I can find a vector associated with that. Okay, so that's defined a vector field. Now the line integral for a vector field is basically compute the f, which is the vector field, and this dr is a small change along direction of my line, and try to compute the dot integral, the dot product, and then compute the integration over the entire line. Okay, how to compute that? To compute the line integral, we typically do is we write the parametric form. It's called parametric form of C. So it's typically given, I write C as a form which is given by r sub t of xt and yt. So here the parametric form has the property that I only have one variable, which is t over here. So there's only even if this is a two-dimensional vector, but we only have one variable, and also the variable is defined from the t naught to tf. That will define all points on the line. Okay, if we have the parametric form of C, now the line integral can be written as a standard integration I mentioned before. So we have to do some sort of change the way we do the integration. So we rewrite this one as integration from t0 to tf. This is the lower bound, upper bound for the parameterized C, the line. Okay, this is starting t and ending t. Okay, now we have to change this f. Of course, we have f is a function of xy, so we just have to replace x by xt and y by it, meaning that I just want to figure the f vector when we use xt yt to replace the original xy in my vector field. And then this dot is r dot t. This r dot t is just x dot t. This is just x dot t and y dot t, and then time dt. That's it. Okay, this is dot product. So we just compute the dot product of these two vectors. Basically, they're all a function of t. So this function also the function, the dot product is also a function of t. So we just integrate that function, this function, with respect to the parameter t from t naught to tf. Now we can find the line integral. So if you look at this, the main idea to solve the line integral, so we have two steps basically. The first step is parametric representation of a line C over here. So what we do is, originally the line is represented by xt, yt, like two-dimensional, even high-dimensional one. I want to write the line just using one parameter, because with one parameter, so I can just reduce the dimension of the computation of the dotting product into just one variable product. Okay, so that's the reason why we do the parametric representation of the line. So once we do that, now this is the idea, we can just rewrite the line integral into a standard single integral, like a single variable integral. Now we can solve for that. Now let's go back to see what is the surface integral. So this the surface integral and its relation to the double integration, because surface integral is sort of somehow related to the double integration. Okay. Now last time, a few lectures ago, we talked about the double integration. So here's how we move from the single integration to double integration. So the single integration, we talk about just a line from A to B along x-axis. Now for the double integration, we talk about an area given by here. For example, if given area in the 2D space, say in the x, o, y domain, I have a surface, an area which is S. So for each point, I define a value associated with that. I call it a z. Okay, a value associated with x, y. So this, let's say this is my x, y, point x, y. Now I have a value associated with that. Let's say this value defines the height, how high this is. Okay, for all the points I can define heights. Okay, different points. So this will, in order to compute the volume, if I want to compute the volume of this base area with the height defined by z, now I can compute this double integration over here, which is the integration. This is called double integration over this area, entire area. I try to compute the fxy, which is the height defined by the height. Let's say this is the height, and over dx dy. You basically, what this basically means is I pick a very tiny area, this dx dy, and assuming the height is just given by a point xy. Okay, will be the same height. I calculate this is a very tiny bit volume for a very small area in S, and with height fxy. Integrate over all the entire surface S area, so I can compute the volume. This I compute the volume, right? Now to compute this, the double integration, so it ends up that we have to figure out this one by using the single line as a standard integration over here. So we just have to figure out two things. One is the lower bound and upper bound for the we have to first divide this one into two steps. One is we consider this is called inner integration. For the inner integration, we have to figure lower bound and upper bound, and then we compute this one. Typically will give a function of y, g sub y. Let's use g sub y, and then you integrate this one. Typically also have a lower bound, upper bound. This will be just numbers, some numbers. This is also some number. So it comes back to the standard integration. So this one comes with some number. So this is we have to compute that. So the key challenges for us to do is try to figure lower bound, upper bound, lower bound, upper bound over here. Okay, then we are done. Okay, so now let's go back to see what is surface integral. So now we just start to look at surface integral. The difference between this guy and the standard double integration and the surface integral is we don't integrate over this one. You can see this. You integrate over a flat area in the x or y domain, while for the surface integral you integrate over a surface. So this surface may not be flat, which means you could consider this as a curve, like a ball, whatever shape you have. So this one is called surface. So surface typically is not flat. Okay, so if you consider this the surface example in the 3D space, so typically surface will be in 3D space, even higher space. So So the surface typically represented by a point. You can have every point over here. Every point, the point is you have x, y, and z. So you define x, y, z, right? You have the coordinate. Of course, for every point you have x, y, z. All the possible points will define the surface. I use the sigma to represent the surface. So also d sigma, okay, is a very tiny little bit on the surface. It's called an infinitesimal piece of the surface. Okay, d sigma is small one. It's not flat. Okay, for this one you see if you pick a very tiny over area dx dy, this is dx dy, very small one. Now it is flat, right? You don't have to do any change, right? If you do dx dy, will give the area. However, here it's a little bit tricky because I have d sigma only. D sigma tells me the surface. Okay, this little piece could also be curved. Okay, so in order to compute this, of course I don't know. The idea is, let's say for example, I'll give you an example what a surface integral means. For example, if this your user umbrella is a surface, right? Your umbrella will try to during the winter, during the raining period time, you get rain, right? At different point, you get the density of the rain. For example, this is density of the rain on different areas of your umbrella. Now you want to see, okay, how much water my umbrella can protect me against. Okay, if I don't have umbrella, how much water I'm gonna have, and if I do have umbrella, how much water my umbrella will collect if I can collect that, right? So this boils down to the problem to compute the integral, surface integral. So integrate over the surface, and you do f x y z. So this is the density, basically the density of my water at any point on the surface. So this ends up having, we can compute this using, and d sigma is the little piece I mentioned over here. Okay, so this is our surface integral. Okay, so how do we solve that? So this one we don't have any existing tools yet. Okay, now the key idea is we want to borrow some concept we learned from here, like parametric representation, and also I want to write this line integral into like a standard integration, for example. And here we hope we can rewrite this one as the first one, the double integration, right? Because like we cannot write in the line integral, of course, right? Or the standard integration is very hard, right? But we hopefully can write this one into sort of like this, the double integration. So that's the hope. Okay. To do so, of course, here we mentioned about two steps. One is the parametric representation. One is rewrite the original one into a form that we know. In this case, I want to rewrite the intuitive idea is first we find the parametric representation of the surface, okay, and then we try to rewrite the surface integral into the double integral that we already know how to solve, how to compute. Okay, so for this video, I'm going to only focus on the how to find the parametric representation of surface. The next slide, I'm going to talk about how we write the surface integral into the double integral so we can compute that. Okay. All right. Now we go to the main part of this lecture. We talk about the parametric representation of a surface. Okay. To give you an idea about what I mean by parametric representation, although I gave you an idea already before, I want to tell you what is a parametric representation and how we can use a parametric representation to rewrite my surface. Okay, so here's a simple example talking about how do I write a line, okay, into a variable, like one variable, right? How do I do the parametric form? Okay, basically here, right? How do I do this? Now if I give you let's say I give you a line, this is my C's line, so okay, so this is my starting point, this is my ending point. Okay, so the basic idea for the parametric representation is I want to map this one into somehow from just a t, which is a straight line, and it's just from t0 to tf. So this is just a one-dimensional. And the goal is for any point, suppose I have a point here, a starting point, I can map the point to some t naught. If I keep on going, I find this one can be mapped to here for some t value, maybe t1. And this point can be mapped to t2, so on and so forth. So you can map everything, all point, until you reach the ending point here, it maps to tf. Assuming every point over here can be mapped to every point over here, not great. This is called a parametric representation. Okay, and we just the map. Of course, in order to do the map, I have to find r sub t, which is the r1t, r2t's, which can represent. This is a representation of this guy. This is the t. The inside the t will be given here. So this is called a relationship. Of course, it's important to figure out what is the r1 function here and r2 function here. So if you have different r1 and r2, you will have different t, the boundaries of t apparently, right? So we sort of want to use the same idea to do the surface, the parametric representation of a surface. Okay, so how can we do that? So here, let's assume I have a surface in the 3D space over here. For example, my goal is, hey, can I sort of use the same idea over here and map the surface into a 2D space, for example? Just, of course, the variable here, variable t is different from x, y. We hope we have a different variable u and v, for example, over here, so that, hey, any point on my surface over here, so I can map it to a point in the 2D space, just a 2D space, okay? Another point I can do right over here, so on and so forth, find all the points. So hopefully this one can be mapped to the 2D, standard 2D space, okay? So what this means, I have to find any point, according to what I said over here. So any point over here, every point over here, on the surface, because this is x, y, z, right? We sort of want to write the surface, any point on the surface can be represented by x, y, and z, which is a function of u and v, u and v, u and v. Of course, the function can be different. Hopefully, any point over here in u and v domain, if I substitute this, compute this for giving u and v, I put it over here, here. Now I can find a point, right, a 3D space point x, y, z, right, figure a point. So this will map back to whatever point over here. So hopefully by exhausting all the possible points over here, I can just find out this will give me, this map will give me entire surface. So that's the goal, okay? Of course, in order to do that, I also have we have a range for u and v, right? So typically, you can say u can be from a to b, c to d, so a and b, c and d, they're constant. A general case typically will be, you have u is a function of v, like u is lower bounded by AV, and b is lower bounded by BV, for example. Then v has to be some constants, okay? Or you can do the very reverse one, is u is less than a and b, and v is less than c of u, a function of u less than d function of u. Okay, that's the same. Okay, that's also okay. So that's the main idea we do, okay? Okay, to understand how we do it, it looks like a little bit complicated. Let me go over two examples to show how to do it, okay? So the first example is, I consider the surface to be, sigma to be the surface of a half ball, on top of a half ball, centered at the origin. Okay, this is ball centered at the origin. I only consider the top, not the bottom one half, with a radius at 1. So the radius for the ball will be just 1. So everything is 1. Okay. So my goal is to find a parametric representation of this surface, sigma. So essentially, according to what I said before, I basically want to find x, y, and z function, and also of course fit a u and a v, maybe something here and v, something over here, so that if I exhaust all possible points defined by this, and for every point I compute this x, y, z function and use that to construct a 3D points that will cover all points of this surface. Okay, that's the objective. Okay. All right, so let's see what we can do. So the key idea is pretty straightforward. It's like, hey, I go this reversely. If I find a one point, let's pick one point on the surface to see, hey, how can I represent any point here? So what variable should I use to define this unique point? Okay, so the idea is, let's pick a point on the surface and see what two variables can be used to uniquely determine this point, right? Okay. So let's say, again, I have this point. So the goal is, let's say I want to x uv, y uv, and z uv to see what we can do, a point p over here. So what variable can define this? Of course, I haven't talked about what is u and v yet, because u and v really depends on how we construct this function, okay? For example, don't look at this one yet. I'm going to talk about how we do it, okay? So if I have this point, any point over here, so what I can do is to determine the point, I start from this point, the very top one, the point along Z. I try to do a curve, a circle, like let the I just cut through. Okay, cut through this one. Let one point and use this point and Z-axis and this point. I want to use cut through this ball, so I get like the this piece, right? This is almost like a quarter of a circle. You have another side over here, and then you go the entire one. Okay, it's just if I draw this over here, it looks like this. We have sort of this. Okay, for this piece over here. So this point actually defined by, this is a P point over here. So the P point is defined by two things basically. One is, okay, if you consider this piece, okay, this is depending on the angle over here is from what is the angle between this x-axis and this one. Because if you move this one, if I have this one point over here, let's say point over here, let's say you're gonna point over here, you do this surface, right? You do this one. For this point, this angle is important. I define this angle by u, okay? This is u, and now this one defines this one. So typically this is u, and also the second variable I'm going to use is between this line in the x or y domain and the origin, connects the origin to this p, and this angle is defined by v, okay? Now these two angles will uniquely determine this p point, because if I tell you, yeah, how much angle you're gonna shift from this x-axis, oh yeah, I'm going to have this in my angle, and also this give me a straight little curve line over here. And if I already tell you the angle, now you need to pick up this point. Okay, so that's why we use variable u and v. So u is this angle I'm gonna use is from x-axis to this line basically. Okay, the second angle is from this line to this line. Okay, that way you need to define this point. Okay, so that's what's the meaning of u and v. Now to auto-compute what are functions x, y, z, so we just figure out, hey, if I give you u and v, what is my x, y, z? Okay, so z is relatively easy because the z is just the height. If you do this is just height. How high is this one? Okay, if you compute the height, this angle is v, so this angle is also v. So the height will be just because the radius here is always 1, right? This is just 1 times sine theta. Okay, start here. 1 times theta is just height. Is height. This is 1 sine v, sorry, not sine theta. 1 sine v is the height. Because look at this one, this is almost like this. This is this angle. Forget about the u here. This is v, right? So the height is, because this is v, this is also angles v, right? So the height will be, this is the radius is also 1, right? This is 1 times sine v. That's why here's 1 sine v. Okay. Now let's go and take a look at this second one. Is x and y. What is the x and what is the y? So if I look at this one, so if you're going to project down here, so this one, right? This is almost at this point I project down to x or y plane only. What do I get? So this is the length. This length is sine theta or cosine theta, as you can imagine. This is cosine theta. So if I drop down here, if I draw the xy domain, so if I project it pointed down to the x or y plane, I do have this. So I do sort of have this. This is the x or y. So I have this point over here, and this length is just this length, right? This is just cosine theta. Then I'm trying to fit xy, okay? The xy here. So this angle is u, basically, right? So x will be just cosine theta times cosine u, because this is x, and the y will be just cosine theta and sine u. Okay, so that's why we get cosine v and cosine u, not theta, sorry. This is cosine u. This is cosine v and cosine u. This is cosine v and sine u. Okay, so that's it. That's why we have this cosine v, sine u, and cosine u, and cosine v, sine u, and this is sine u. Okay, that's the way you need to determine. If I give you these two angles, you can uniquely decide what is the point over here. Okay, this point is on the surface. Okay, Alright, so now it becomes the second problem. How do we find the lower bound, upper bound for u and v, and the bound of u and v, because that filters the region, right? So because if I look at this one, so in order to exhaust all the possible points on the surface on the top of that, so what variable is u we should select? This is my u, right? The u has to cover from 0 to 2 pi. You go to entire, right? You can go to from here x, you go counterclockwise and do backwards and go back to itself. So that's why you can see u is from 0 to pi, 2 pi, and v is for each one. I just only use 90 degrees over here. I just start here from to here, right? I don't go to the other side. Otherwise, you double count, right? From 0 to pi over 2. Okay. The other option, this is one option. The other option you could also do is I can let my u to be 0 from pi, which means I only my angle only go from here, go backwards, and then go to the other side, right down. Okay. Of course, in order to do this, you have to your v has to go all the way to the other side. You have to cut over the other side, right? The other option is you can have u is from 0 to pi and v also from 0 to pi. So for the same representation, you can pick two different options for u and v. They will give you the same representation of the surface. Okay. So I hope this is a little bit, it's a little bit complicated. I hope we give you a lot of ingredients about how you compute, how do you find a parametric representation of a surface. Okay, so next one is a little bit simple. So this one, I want to compute, let it be this is a second example. Let sigma be the surface of a cylinder centered around the axis. Okay, the radius is 1. Okay. The top of the cylinder ends as 2, so here is 2. The bottom of the cylinder ends start as this is 0, so this is just 0. And I want to find a parametric form of this surface. And of course, I'm going to talk about outside surface. I'm not talking about no top or bottom. Okay, only about the side. Okay, so I want to find a parametric form of this sigma. Okay. Again, like I said before, okay, we just want to find for any point. I pick a point on the surface over here. My goal is trying to figure out, hey, for this surface, for this point, how do I find it uniquely a point x, uv, y, uv, and z, uv, such that this point can be uniquely determined. Okay, so determine this point, apparently we have to determine how high it is, right? So apparently this height is determined by what z value we have. So the last part is fairly easy. So it's just z, right? You just have z over here. Z will be the same height as p, okay? The second one is how do I find this point, right? Okay, in order to find the point x, y, we just project this point back onto just to the bottom of here, right? The present point. Because this point is on the surface, you just project back directly onto this circle. This circle, the bottom of the circle, right? This point. This point and this point, so this point p prime and p, they have the same xy. So this is xy 0 a point. If this is xy some value, let's say 1.5, whatever. The only difference is the z value, but xy value is the same if we project down to the xy plane. So that's why let's compute this point p prime, because it's already in the xy domain. So we can, if we know the theta angle over here. Yeah, according to what I mentioned before. So yeah, this is the x value will be just this p, the length here is always 1, radius 1, right? So this is 1 time cosine theta, so 1 time cosine theta, and the y-axis is 1 time 1 time cosine theta x, 1 time sine theta is y, and z is still the z. So you sort of see here my u and v will be u is theta and v is z. I have two variable. You can change a variable. You can say, hey, this is my you can change this one to cosine u and sine u, and z is v. That's fine. So by looking at this one, so the theta's angle, yeah, of course the angle should go back from 0 degree to 260 degree, which is from 0 to 2 pi. And z, yeah, you start from 0 to 2 because the bottom one is 0 and the top is 2, and that will define all point on the surface of the cylinder, excluding the top and bottom. Okay,